Assalamualaikum warahmatullah. So today is our lecture 9, and in this lecture we'll be covering the 4 fundamental subspaces of a matrix. Okay, so before that I want to recap some of the topics, and the first topic is independence. So we already know what independence is from the perspective of linear algebra, right? So in simple words I can say that the columns of a matrix are independent if they are not the linear combination of any other columns. Okay, so if I give you a matrix A, and if I say that okay, this is a m by n matrix, and m is less than n. Okay, so from this property we can say that this, so there are more unknown than the there are more unknown than the than equations, right? So in this case like there are non-zero solutions to ax equals to 0, right? So because there will be free variables, and because some of the columns will be a combination of other columns. So if I give you the formal definition of the independence, I can say that like vectors, if you have vectors x1, x2 up to xn, then they are independent if no combination gives 0 vector except the obviously the 0 combination. Let's put it in bracket. Okay, so if some other combination like other than the 0 gives a 0 vector, then the vectors are dependent. Okay, for example, let's say you have this one, let's say this is your v1, and let's say this is your v2. Okay, so let's say v1 is v2 is twice as v1. So from here we can say that 2v1 minus v2 is equals to 0. So in this case v1 is, or v2 is dependent on v1, or like they are dependent on each other, they are not independent. Okay, they are not independent vectors. So if I summarize the whole thing, so if you have a matrix A equals to, let's say this is column v1, this is column v2, so up to vn, then I can say that they are independent, the columns, they are independent if the null space of A is only the 0 vector. For example, let's say you have this matrix 1 2 3 4 5 6, then let's say 5 7 9. Okay. So okay, let's take some other column, let's say 0 0 1. Okay, so we can find no other combination other than the 0 that gives you actually this the right hand side 0 0 0. Okay, there are no other combination other than this one. But if you take 1 2 3 1 2 3 4 5 6, then let's say 5 7 9, then if you take 1 1 and a negative 1, you will get a 0 0 0. So in this case the columns here are not independent, but in the previous case these columns are independent. Okay, so in this case the rank of the matrix is equals to the number of columns. So the other case is they are dependent if AC, C is for column, AC equals to 0 for some non-zero C. Right, so in this case the rank is less than n. So this is bit of a formal definition, but like if I break the concept of independence in simple words, this is simply as if you have a matrix, there are some columns in that matrix, and those columns are independent if no column is a linear combination of any other column. Okay, and they're dependent if you get one column that may be a multiple of another column, or that may be a linear combination of any other columns. Okay, like just in this case. So so this is the core idea of independence. Okay, so now we'll see what is a basis. So we have to know about basis, but before that we need to know about a span. So we already know about a span, right? So let's say you have some vectors v1 v2 to vn, and if all these columns are independent, then the space that they can cover is the span of those vectors. Let's say you have three vectors, and those vectors are 1 0 0, and let's say 0 1 0 and 0 0 1. So you have these three independent vectors or three independent columns. So as you all know that these three vectors, or the linear combination of these three vectors, can cover the whole R3 space. So the span of these columns are, or the span of these columns is R3. Okay, so if we had two columns, let's say if we had this scenario 0 2 0, so as you can see this this column vector and this column vectors are fundamentally same. Okay, so in that case you cannot span the whole R3. In that case what you can span is that you can span a subspace which is a plane in R3. If you had only these two vectors. Okay, All right. So this is the main idea of spanning a space. So when you have vectors, so let's say v1 v2 up to vn, so they can span a space, means the space consists of all the combinations of those vectors. Okay, for example, a span, the example of a span is the column space the column space of any matrix. So this span column space is spanned by the columns of a matrix. Okay, so the columns, so the span of the columns of any matrix is the column space. All right, and the idea of basis comes from the idea of span. Okay, so the fundamental vectors or the fundamental column vectors that span any subspace or any vector space is known as the basis. Okay, so if I give you a formal definition, it is basis is the fundamental set of vectors that can span a space. For example, for R3, one basis is, so always remember that basis is not any vector, basis is a set of vector. So for R3, one basis is 1 0 0 0 1 0 and 0 0 1. So these are the fundamental set of vectors that can span that can span the whole of R3. Okay, so in R n vector space, n vectors give basis if the n by n matrix, is invertible. So what I wrote in here is that suppose you have a n by n matrix. Okay, suppose you have n by n matrix, and that the column space of that matrix would be R of n, if this matrix is invertible. That means all the columns of that matrix is in fact independent. Okay, so to be a basis, I think you already understood that to be a basis for a space, you have to have two properties. Okay, so basis for a space is a sequence of vectors, let's say v1 v2 v3 up to v of n, with two properties. What are those two properties? First one is they are independent. The span vectors have to be independent, or the basis vectors have to be independent. They are independent. And second condition is, as they are a basis for that particular space, so they have to span they span the whole space. All right, so I previously gave you one example of a basis of R3, and that was 1 0 0 0 1 0 0 0 1. So is this choice unique? So my question is this choice unique? The choice of picking the basis vectors for any space, is this unique? The answer is no. As long as you fulfill these two conditions, your choice is not unique. Like you can take any vectors. Like for R3, you can take any other three independent vectors that can span the whole space. For example, I could take 1 2 3 4 5 6 and 0 0 1. If I can prove that these three columns are independent, so then yeah, so if I can prove that these three columns are independent and they can span the whole R3, of course they can span the whole R3 because with their dimension is 3, so they're like you have to have three vectors to span the whole of R3, so you have to have n vectors to span the whole of Rn, right? So one more question in this regard is that if I just take only these two vectors, are they still one basis of R3? So in R3, what we have is that we have this image, let's say, and let's say for this 1 2 3 we have this vector, and for this 4 5 6 we have this vector. Okay, so what are all the combinations of these two vectors? The combination of these two vectors is, you already know that it would be a plane, right? Only if we had another vector we could span the whole of R3. So I can say that though these two vectors are independent, but they cannot span the whole of R3. So these two are not a basis of R3. We need to have another vector to span the whole of R3, and then it could be considered as a basis. But yes, they can be a basis for a subspace created by a plane in R3. Yes, so 1 2 3 4 5 6, these two columns can be a basis only for this plane, or it can be written as a subspace in R3. So for this plane, these two vectors can be considered as a basis. Okay, so there are millions of possibilities for a basis. Okay, but like there is one common thing for all the bases. So what is that one common thing? One common thing is every basis for this space has the same number of vectors. Okay, so whatever choice you might make, you'll always need three vectors to span whole of R3. So in other words, you'll always have to have three vectors inside the basis to span the whole of R3, or to be a basis you need to have a set of three vectors. Okay, so this is common for all the bases. So in R6, for example, in R6, if I take 7 vectors, of course with 7 or let's say 6 elements each, if I take 7 vectors, that is too many, for the basis. And in R6, if I take 5 vectors, that is not enough for the basis, right? So I need to have that perfect number for the basis. Like, you need to have exactly 6 vectors. To be a basis, or there should be 6 vectors inside the set of bases to span the whole of R6, right? So for this R6, 6 is the perfect number, right? And this perfect number is known as the dimension, whatever you might say, dimension of the space. Okay, so this is the definition, or this is the concept of dimension of a space. So if I want to give you a formal definition, that would be the minimum amount of the minimum number of vectors that can span the whole space is known as the dimension. Okay, and that set of vectors are known as basis vectors. So this is very important. So if I take one matrix and try to give an example of that, of all these concepts, that let's say you have this matrix A equals to 1 1 1, 2 1 2, 3 2 3, and 1 1 1. So as you can see, the first column is independent. Let's take the first column as an independent one. The second column is not any combination of the first column, so this is an independent one as well. But the third column is the addition of column 1 plus column 2, and this is basically column 1. So these two are not independent. So there are 2 independent columns and there are 2 dependent columns here, right? So if I ask you what is the span of these column vectors, so as there are 2 independent columns, so the general answer is the span of in the first portion of the lecture I said the most common example, or the easiest example of any column, is the column space of any matrix. So the span of the columns of any matrix is the column space. So the simple answer is the column space. Column space. And if I want to give you a more specific answer, the answer would be, there are two free columns here, there are two independent columns here, and the span is basically all the linear combinations of these two columns. So it can be C into 1 1 1 plus D into 2 1 2. So there's another way of writing this, and this is the combination of 1 1 1 and 2 1 2, all the combination of 1 1 1 and 2 1 2, right? So yeah, so the second question is, are these columns independent? No, these columns are not independent, because if I want to give you the formal definition, the answer is the null space of A has a non-zero solution because there are free columns here. Alright, so these columns are not independent. So what is the basis of the column space? What is the basis of the column space? So the basis of the column space is the minimum number of vectors that can span the whole column space, and those minimum number of those minimum vectors are the first column and the second column. So the answer is 1 1 1 and 2 1 2. Alright, so these are the two columns that can be addressed as the basis of the column space. The third question is, what is the dimension of the column space? So as per the definition, the minimum number of vectors that creates the basis, okay, or that can span the whole space. In this case, the case is the column space. So the dimension of the column space is basically I think you already understood that this should be the number of the number of independent columns. Okay, so the number of independent columns actually specifies the rank of any matrix. Okay, so in this case, the number of independent columns or the rank of the matrix is basically 2. So this is the dimension. So this is the minimum number of this is the minimum number of column vector with which you can span the whole column space, which is this case. And as you can see, there are 2 columns here. So 2 independent columns and 2 independent columns to span the whole column space. So the rank is 2 and the dimension of the column space is 2 as well. Okay, so for all the cases, dimension of any column space is basically the rank of the matrix. Okay, so the last question is, what is the dimension of okay, what is let's write this in a big font. So let's say you had this matrix. Sorry for the delay. So the matrix, initial matrix was this one, 1 1 1 2 1 2 3 2 3 1 1 1. So the last question is, what is the dimension of the null space? So you have to think that what creates the null space first. Okay, so as you can see, as you know, that these two columns are free columns. So these two columns actually gives you the whole column the whole null space. Or for these two columns you will get two spatial solution, and let me tell you, the two spatial solutions are, so the whole null space is basically the linear combination, all the linear combinations of -1 -1 1 0 and -1 0 0 1. So you already know how to find the null space. Please do it. As these two columns are free columns, we set these two columns as 1 0 and 0 1. Okay, and the whole null space is the linear combination of these two columns. So what is the minimum number of column vectors that give you this null space? The answer is 2. So the dimension of the null space is basically 2. We can say, in other words, that the dimension of any null space is basically the number of free columns of a matrix. Alright, so it should be n minus r. Okay, so this is true for any case. So I think you already got the main ideas of the dimension and the basis vectors. So let us solve the bigger question, the 4 fundamental subspaces of any vector. The 4 fundamental subspace of a matrix. So okay, so you already know about 2 subspace of a matrix. The first one is the column space. So if you have any matrix, you would have a column space for that matrix. If you have a column space, then you will have a null space of that matrix. And there are other 2 subspaces, and those are the row space and this is the zooming. Amazing. And the last one is the left null space. So what are these? We will get to know. So first, let's know about all the fundamental subspaces through an example. Okay, so let's take a row reduced echelon form of a matrix. Okay, so let's say we have R equals to 1 0 0. So this is just because of the better understanding of which columns are pivot columns and which columns are free columns. Okay, so we'll work this out with another matrix, no worries. So let's say these are the columns. Okay, so as you can see, this is a pivot column. Okay, yeah, this is a pivot column and this is a pivot column. So these columns here are free columns. Okay, so if I talk about the column space of A, so the rank here is getting very difficult. So the rank of this matrix is, as you can see, there are 2 pivot columns, so the rank is 2. Okay, so if you have the rank as 2, what is the dimension of the column space? So the dimension is also 2. This is the same as rank. So what is the basis for a column space? So the basis for the column space is the first column, this column and this column, the first column and the fourth column. So the pivot columns are basically the basis. Okay, so if I write the basis for the column space, this is basically 1 0 0 and 0 1 0. These are the basis. Now let's work with the null space, of A. So think about the spatial solutions of A that solves A equals to 0. So there are 3 free columns here, so there would be 3 spatial solutions, right? And the combination that goes for the free columns while finding out the spatial solutions would be like setting one free column to 1 and other free columns to 0, right? So the rank of this null space would be the number of free columns, which in this case is 5 minus 2 is 3. Okay, so the dimension of the null space is also 3, right? So there are 3 spatial solutions, and as the dimension is 3, so there should be 3 basis vectors for that null space, and for that basis vectors you have to find out the spatial. So the basis is basically the three x spatial. So you have to find out the x spatials from here. You already know how to find the null space, right? So now we'll have to work with the row space. So from the name, so this is column space, null space. So from the name you already assumed that the row space is basically the space spanned by the rows of any matrix. Okay, so this is written as C column space of A transpose, because whenever you transpose this matrix, you will get the rows as the columns. Okay, so let's write this down. So A transpose is basically 1 3 5 0 7, then 0 0 0 1 0, then 0 0 0 0 0. So from this you can see that what is the rank here. So the rank here is 2, as we got 2 pivot columns here, but this is not a pivot column, these are all zeros here. So the rank here is 2. So what would be the dimension of the row space? It should be also 2. And what should be the basis for the row space? There should be, in this case, column 1 and column 2. So we can write this as 1 3 5 0 7 and 0 0 0 1 0. So the summary is, whenever you transpose the matrix, or whenever you transpose any matrix A, you convert the rows into columns, right? So after that, if you find the span of that column space, you will get the row space, because you made the rows into columns, right? So as you can see that in this case, the column space of A transpose is basically all the combinations of 1 3 5 0 7 and 0 0 0 1 0. Right. So I think the idea of row space is clear. Row space is basically the span that is covered by the rows of any matrix whenever they are considered as the columns. Okay, so if you consider the rows of a matrix as columns, then the area that can be spanned by those columns are basically the row space of a matrix, because those columns are achieved by converting the rows of the matrix. Okay, so I hope this concept is clear. So the last one is the left null space. Left null space, sorry. How does this thing work? The left null space. So the left null space is basically the null space of the row space. Okay, so this is written as this, the null space of the row space. So let's say you have a y equals to 0. So y is basically the null space or the spatial solutions. Okay, so now if you transpose the whole thing, then you'll get y transpose and you'll get the A transpose here. The orders are changed here from the rules of matrix multiplication. Okay, so this is also 0. So as you can see, So this was the special solutions, or all this combination are basically the null space. So as you can see, this is the row space, and this particular thing here has come to left, so the null space, comes to left. So that's why this is known as the left null space. So left null space is basically the null space of the row space. So if you have R transpose equals to, you already know what is R transpose, so 1 3 5 0 7, then 0 0, what was it, 0 0 0 1 0, and 0 0 0 0 0. So what is the null space here? So so there is only one free column here, and for that free column you set this as 1, and what you will get is the null space for this particular matrix is 0 0 1, all the combinations of this one. Okay, or this can be written as this. So this is the null space of R transpose. Okay, so the dimension is definitely, so the dimension of the left null space is basically the free columns or the number of free columns, the number of free columns in A transpose, so which in this case is is 1. So the answer is 1. So it can be rewritten in another format, or in another expression, that is, it is basically M minus R. Alright, so this would be always this case would always be true. So in case of a matrix of n by n order, with rank R, then its left null space has the dimension M minus R. Okay, so it will be always the case. Yeah, so in this case, so the number of M was, so we have to be careful, this M is not for A transpose, this M is actually for A, this is the M of A. So what was the M of A? The M of A, or M of R, was 3, right? So 3 minus, the rank was 2, so 3 minus 2 was 1. Now why is it the case? Because Oh, this is actually true for, yeah, this is true for anything. So if you so actually as you can see that as the elimination is done on this matrix, so any independent matrix or any independent column actually have non-zero values, and if you have any independent row, so if you have any independent row, that would have non-zero value, and if you have dependent row, you will get zeros for that row because you are doing some row operation on that particular matrix. Okay, so these are the four fundamental subspaces of any matrix A. Okay, so I think from all this discussion, one thing is clear, that if you have a particular matrix, let's say you have 4 columns, if this matrix is m by n, then there are 3 elements in each column, right? So the null space, the column space of A would be in Rm, right? So there are 3 rows here, and the column space of A would be in R3. Okay, and the row space would be in Rn, because as there are 4 columns, if you transpose this matrix, you will get 4 rows, right? So the row space would be in Rn, and basically if you find any solution here, like if you try to find 0 0 0 0 for which for which combination will get 0, or if you try to find out the null space, you will have how many elements here. So the elements would be there would be 4 elements, right? So same as the number of columns. So the null space of A would be in, definitely there are 4 columns, so in this case m is 3 and n is 4, so the null space of A would be in Rn. And how this thing work? So you cannot write. Look at the null space of A transpose, or the row space would be in, so it will be connected to the column space Rm. Now the important thing is, in Rn the dimension of the row space if the dimension of the row space is the same as rank, right, and the dimension of the null space would be n minus r, the column minus the rank. And in Rm, the dimension of the column space is r, or the rank, and the dimension of the left null space is m minus r, right. So the column space and the left null space are connected because they are in the same vector space, and the row space and the null space are connected because they are in the same vector space. So if I try to draw the bigger picture here, it would be, so this is, let's say this is the column space of A. So the dimension is the same as the rank, and this is connected to the left null space. So in this case the dimension is in this case the dimension is m minus r, okay. And if I try to draw it for the row space, the row space is basically in Rn, so the dimension is same as rank, and it is connected to the column space because they are in the same vector space. They're not in the column space, they're in Rn, okay. So the dimension here is n minus r, okay. This relation is because of m by n matrix of R rank, and these two subspaces are in Rn, and these two subspaces are in Rm, okay. So this is the big picture. So let's solve today's lecture's last problem. So let's say you have a matrix A equals to 2 minus 4 minus 1 2 and minus 3 6. So for the column space, as you can see, there is only one independent column here, and other two columns are basically some multiples of the first column. So the column space has this span of all the linear combinations of the first column. The basis is the first column, the dimension is 1 as the rank is 1, and the so these are the three parameters. What about the null space? So for that you have to find the null space. What is the null space? So as there are two free columns, so you will get definitely two two spatial solutions for that, and those spatial solutions are x spatials are, please do it by yourself. So half 1 0 and 3 by 2 0 1. So the span of the null space would be all the linear combinations of these two columns. So these are the bases, and the dimension is the number of bases or the number of free columns here. So it would be 2. Okay, this is the null space. What about the row space? What about the row space? So for the row space, the span is basically the number of independent rows. Okay, so how many independent rows are here? So for that, please transpose the matrix. So if you transpose it, you will get 2 minus 1 minus 3 and minus 4 2 and a 6. So you can clearly see that this column is multiple of this column. Okay, so this is not an independent column. So the independent columns in A transpose actually gives the basis for the row space, right? So 2 minus 1 3, so 2 minus 1 minus 3, so this row actually gives the basis for the span of row space. So the span would be 2 minus 1 minus 3. So this is the basis, and the dimension is only 1. Okay, what about the left null space? So left null space is the null space of the row space. So the left null space, so if you just try to find the null space of this matrix, you will get it. You will get the left null space of A. Okay, so what is the one? So there are two columns here. So there would be, and this column is dependent. So there would be this is one free column. So for this free column, you will get one spatial solution, and that particular spatial solution is x spatial is, or if I break it down, the row reduced echelon form of A transpose is basically 1 0 0 minus 2 0 0. So the spatial solution for this is 2 1. So the span of the left null space is basically all the linear combinations of 2 1. So this is the basis, and the dimension is 1. Okay, so is this true that in the previous part we wrote that the dimension of the column space of A is basically the rank of the matrix, the dimension of the row space is basically the rank of the matrix, the dimension of the null space of A is basically n minus r, and the dimension of the left null space is basically m minus r. Is it true? So let's verify it here. What is the rank of the matrix? So the rank of this matrix is 1, because there is only one pivot column here. So this is 1, this should be 1, and this should be 1. Is it true? So the row space has the dimension 1 and the columns has the dimension 1, and the dimension of the null space should be, so how many columns are here? 3 minus 1, this should be 2, and there are 3 columns and 2 rows, so 2 minus 1, it should be 1. So let's check. So dimension of the null space, so where is the null space? So here is the null space, the dimension is 2, and the dimension of the left null space should be 1. So the dimension of the left null space is 1. So this is verified. Okay, so this is, so if I give you one matrix in the exam and ask you to find out all the fundamental subspaces of that particular matrix, you can do it if you watch this lecture carefully. Okay, so we'll see you in the next class, inshallah. Assalamu alaikum.